that entry to the Technion will only be possible with a green sign. Okay, so if you don't have a green sign, you have to do a corona check, because otherwise you can't enter to the Technion. I will be in exam, of course, and everyone who has a question, I will take him to the class with the Zoom in with Alan, and you have to you can speak a few minutes and ask every question you have about exam. Okay. I think if you have another question about how be exam, you can ask me. If not, so Alan will explain you about exam academically. Okay.
Okay.
Okay. If you want ask me in mail, of course, I always answer very quick. Okay. If you don't have a question, Alan, I want to tell you that Shana Tova, because I don't think that I will see you until then. And then Alan, I want to see you in Israel, but I don't know when.
Well, I'm trying again to come in December. We'll see if Israel lets me in.
Okay, so that's it. Okay.
Shana Tova.
Shana Tova,
Shana
Marina.
Tova.
Okay. And Marina, you're taking attendance. You're taking care of the attendance today. Okay.
Yes. Zero.
Okay, very good.
I finished. Yofi. Bye.
Okay. Bye. Okay, so let's talk a little bit about the exam. I, of course, think the exam is very straightforward and very easy, but then I would expect that I wrote the exam. The exam is open book, open note, open computer. You can bring your computers into the classroom. In fact, I strongly suggest you bring the computers into the classroom. I think somebody needs to mute their. I think somebody needs to mute themselves there. Okay, so I strongly recommend you bring your computers in there, because I'll tell you right now, there are going to be Beam and Elastic Foundation questions on the exam, and it's not that easy to do it by hand. You can do it by hand. I know people who do it by hand, but it's a lot easier doing it on an Excel spreadsheet as you've done the homeworks and assignments and things like that. So the only thing that you're not allowed to do on the exam is check with each other. You can't work together. There's no joint work. The work has to be your own work. But as far as I'm concerned, all the files that I've uploaded to a Moodle on the website you can use. You can use your computer files. You can use that. I'm going to be available for questions, but I'm not going to give you the answers, but I'll certainly be able to answer any questions that you may have. Okay, so the way the exam is going to be structured, there are approximately 30 questions, ranging in value between 3 and 4 points each for the most part. Most of the questions are multiple choice. There are about a half dozen questions, 6 questions at the end, which are fill-in. You just have to fill in some answers, but most of the questions are multiple choice, including all the problems. Now, don't think that it's going to be that easy, because I put some of the answers close to each other, so you really do have to solve the problem correctly. Most of the equations that you're going to see are equations that I've given work problems. The class problems that I've given you are going to be very, very heavily there. So again, if you want to study for the exam, I strongly suggest the best way to study for the exam is to go over and make sure you understand all of the problems I've given you and I put on Moodle with the answers. Again, please feel free to email me. I know a lot of you do email me. The only thing, of course, is because we have the Chagim coming up, I'm going to have to work around the Chagim when I answer my questions. That we can't avoid this time of the year. And now there also will be some word problems, some text problems taken from the lectures and the notes. Anything, I went over the exam the other day to make sure that in fact I did cover in class every question that's going to be there. So I know I've addressed all the questions in class, and also they should all be in the notes as well. Even though, of course, going through, there are a lot of notes, so going through the notes takes a lot of time. So that's why I really hopefully everybody will understand and work with the problems. For what it's worth, this is basically the same exam I've given to 2 previous groups before, and for the most part, people have done well. The general grades on my exams are pretty good. Some people do struggle, one of the reasons I don't think it takes 3 hours to do the exam. I know I routinely have people finish in 2 hours, without any problem. But I also know that there are some in the class who have a little bit more difficulty with English than others. So I give the 3 hours for those that I know are struggling with the English, and to make sure they have enough time to do that. You don't have to take the 3 hours. By all means, if you finish in less than 2, you turn in your exam whenever you're done, but you will have 3 hours available, which should be plenty of time, even for those who are not as comfortable with English as others. Anybody want to ask me any questions about the exam other than don't ask me what questions are going to be on it, because I already told you as much as I'm going to tell you.
Can I have a question, please?
Sure.
So if I solve the problems in the Excel files, do I have to give you the Excel files also?
No.
Okay.
If you're not sure about the answers, you can. The exam has some blank pages at the end for notes. And if you feel that you're not sure you're right, and if you want to just write down what you did on that paper, and if I see you get something wrong, I'll check and I'll take a look to see what you did. And if I see there's some error in there, that's a careless error or something like that, I will give partial. I can give partial credit. But generally speaking, you should be able to get the answer. Let me put it this way. If you get an answer that's not one of the 5 choices, this is the advantage you have. There are going to be 5 choices. If you get an answer that's not one of the 5 choices, then I'll tell you right now you did something wrong, go back and check. Because I promise you the correct answer is going to be one of the 5 choices. So it should be, from that sense, it should be fairly straightforward. If you got the right answer, you see it, it's there.
We have something like 5 to 6 major subjects in this.
Yes.
If you can emphasize what kind of subjects should we put on?
If you want to prioritize your study time, prioritize the class problems I gave you. The problems that I put in Moodle, the ones where I have the exam problem, and you have the answers in the spread. There's an Excel spreadsheet for the problem and answers on that. That you should really be very familiar with all those problems, because I lean heavily on that. That's not all the questions. The other material is scattered throughout, but many, many, many of the questions are going to be those kinds of problems. And again, the beam and elastic foundation one. And I'll tell you right now, I'm going to expect you to know both one wheel and 2 wheel problems. So so that there's a sort of a study hint for you. Make sure you understand. And again, the Moodle problem on beam and elastic foundation has both a 1 wheel and a 2 wheel set of questions and examples there. So you should be able to follow that as well.
And the other subjects?
The
Not
other
only-
subject is what we covered in the class.
Okay.
I can't make it that easy for you.
Okay.
Again, I'll emphasize the fact that this is very similar to the exams I've given to the two previous groups that have gone through this program. And for the most part, grades are generally pretty decent, pretty good. I really expect and hope everybody does well in this exam. I'm a person who believes that everybody should do well in an exam. I don't need to fail people. In fact, if people fail, I consider it more my problem than your problem. So I think you'll all do well in the exam. And then again, of course, you get me again in January, and we'll do another set of material. But let's do one thing at a time. Okay. Have any more questions about the exam? All right. So let's take this last class, and I'm going to start off this last class talking about slab and direct fixation track. And I know we have some people out there who do a lot of work in that area. So, you know, if you have any comments or suggestions and you feel you want to jump in, feel free to comment. I actually added this last year because I was getting some comments from some of the people saying that there are a lot of people who work with the transit systems with Jerusalem and with Tel Aviv, and not only Israel Railways. And so they wanted to make sure I covered some material relevant to direct fixation, slab, embedded track. So I will start off with that. I'm going to try to address beam and elastic foundation theory. I'm going to try to address continuously welded rail theory a little bit today. And then if I have time, and I suspect I won't, but if I have time, I'll try to finish up with ultrasonic testing of rail. But in the meantime, I want to start with the slab and direct fixation track. So let me share my screen and see. Here we go. Move this out of the way. Okay. Get my highlighter out there. Okay. So we're going to talk about transit and slab and embedded track. We're going to try to cover a lot of material that's of relevance, particularly when you're dealing with transit systems. So in general, these track types fall under the broad name of ballastless track, track without ballast. We spent a lot of time talking about ballasted track. We spent a bunch of time talking about ballasted track, and I think you've had other lectures on ballastless track, but I don't think you've had that much on ballastless track, track without ballast. So we're going to talk about that today. The two major types of non-ballasted track are called, in general, called slab track and embedded track. Slab track is usually made out of concrete slabs, either cast in place or continuously cast or precast and brought in track. but usually consists of some form of concrete slabs of some sorts. Embedded track is track that's laid usually in the street. So all you have to do is go to Jerusalem and walk down Rehov Yafo, and you'll see lots and lots of embedded track. That's track that's built into the street itself. Slab track can be further divided into what we call direct fixation track on slab and cast and placed ties or tie blocks. And we'll talk about each of these in turn. So let's start off with the rail. Conventional ballasted track uses a standard T-rail section, which you spent a lot of talking about, which is also called a Vignoli or flat bottom rail. It says of, it should be or flat bottom rail. So Vignoli rail, flat bottom rail, T-rail, that's all our standard rail section. That's self-supporting, has a stable base, has a single large head, and has a fairly significant bending moment of inertia. Embedded track, and there is embedded track does use T-rail, and I will show you some embedded track that does use T-rail, but they also use groove or girder rail, and you'll see that term both used again. So groove or girder rail we spoke about. I'll show you a few more examples of that in a minute. The advantage of groove or girder rail is it comes with its own flange way. So the flange way for the groove or girder rail has a guard for the back of wheel flange contact, so it doesn't go riding onto the street where embedded track lies. Slab tracks always use T-rail. You really will not see groove or girder rail in slab track. In fact, the only place you're really going to see groove or girder rail is in embedded track. Guardrails and restraining rails, we've already spent some time talking about that. You tend to see a lot of guardrails in slab track environments, and you tend to see restraining rail in very sharp curves in slab track. So again, just as a reminder, this is a groove rail where the wheel sits there. And this is most commonly used in an embedded track of some form or another, where you can run the pavement of the street, be it paving blocks or asphalt or cement or whatever it is, you can run it to the back of the guard here and to the rail here. So again, I've shown you pictures in the past of embedded track. These are fairly classical types of embedded track structures. Groove rail, just like standard rail, groove rail comes in different sizes, shapes, and weights. Usually the name implies what the weight is, but not always. It's one of the problems. So like a very common groove rail happens to be RIN 59, which is a fairly common groove rail. So that does happen to be 59 kilograms per meter. RI 60 happens to be 60 kilograms per meter. But you can see I have an NP A4AS, which is 62 kilograms per meter. And I have a 35 GP, which is 55 kilograms per meter. So it's you gotta be it's a little bit deceiving. You don't always rely on the name to tell you the weight of the section. Other than that, dimensions are fairly similar. You can see the heights range from about 150 millimeters to about 180 millimeters. The base range from about 140 to about 180 millimeters. So you get you have a fairly standard type of configuration here. head width ranges from about 110 to about 100 and almost 120 millimeters wide. Again, very often you pick the rail section based on availability and cost. Groove rail section tends to be more expensive per ton than regular T-rail. For among other reasons, they're not rolled as often. They're not rolled in as large quantities. When a mill rolls UIC 60 rail, they'll roll very large quantities of UIC 60 rail. When a mill rolls RI 59 rail, they'll roll relatively small quantities, usually for somebody's order. If a metro comes along and wants to order, a couple of 50, 100 kilometers worth of rail, in the rail steel world, that's not a lot of steel. So you think 100 kilometers of rail is a lot of rail. In the rail steel world, that's not a lot of rail. And very often the mill has to change its rolls to accommodate this. And the groove rail section is a little bit more complex to roll than a regular T-rail section, just because of the groove in the center of the head. And so you do tend to pay a little bit more for the groove rail sections. As I indicate, what kind of rail you use really varies with your design configuration. But for the most part, you're going to see grooved rail and some sort of embedded rail type of environment. And direct track will almost always have flat bottom rail, be it in the on ballast or on ballastless slab tracks. Depot tracks will vary depending on, again, the design of the depot. If it's an embedded track, it'll be a grooved rail. If it's a slab track, it'll most likely be a flat bottom rail or T-rail. Okay. We spent a lot of time talking about guard and restraining rails, so I'm not going to, I'm just going to quickly just go through some of that. Again, remember the guard rail is the non-contacted rail whose this purpose is only there to prevent a vehicle falling off a bridge or falling off of an embankment or falling off of an elevated structure in the event of a derailment. Restraining rail is designed to always be in contact with the back of the wheel flange. And the purpose of the restraining rail is to take some of the high lateral load off of the outside rail and distribute it between the two rails so that you don't have an excessively high lateral force on your outside rail on very sharp curves, which is what, of course, what happens. And so you pick up part of the, so your lateral load is again divided between the outside rail and the inside rail. So again, you see that only in very sharp curves. Okay, so again, guardrail is a non-contactive rail to prevent derailments. You see it on bridges, for example. Israel Railway standard is to have guardrails on every bridge on the railroad. In fact, I recently was involved in the rewriting of the guardrail standards for Israel railroads. We have, they have to be strong enough just to hold a train in the event of a derailment. You see them on sharp curves. You'll see them in mountains territory. And more commonly, you see it located in the center of the track. Sometimes you'll see it off of the low side of the curve, non-contact mode, but mostly you'll see it in the center of the track. So restraining rail, again, is designed to be in contact with the wheel on the low side back here. We see it most commonly in transit tracks. I really haven't seen restraining rail in any serious major application on railway track, but where I see them is on metros, where you have very, very sharp curves, and that's that's where they're common. In an embedded track, oops, sorry, let me go back. An embedded track, you actually get a little bit of that effect by the outside portion of the railhead, the guard portion of the railhead. So that actually can function as a form of restraining rail in very sharp curves, even though most of the time it's not in contact. In fact, you got to be very careful with embedded track that you don't have excessive wear out here, because you have a very thin section. And if you have excessive wear in this portion of the girder rail, of the grooved rail, you can have yourself a little bit of a problem. So as I indicated, it splits the lateral force between the outside and inside. It also introduces new wheel wear, because now you have wear on the outside of the wheel flange. So all of a sudden, now you're getting wear in this portion of the wheel flange as well, where normally you don't see wear. But that's, yeah, so you have to be really careful about getting excessive wear. And now you have wear on this side of the flange and on this side of the flange, and you can very quickly have excessive wheel flange. And in general, in metros, thin flange is the most common reason for replacing wheels. When this flange gets thin, excessively thin below the wheel standards, allowable standards, that's a major reason for either replacing or truing, machining the wheels to get a new profile back. Restraining rails come with in various different designs. In this particular case, you actually have a modified running rail with braces holding it in place. Another design that you will see is a design such as this, which this is now my restraining rail. Oops, sorry. This is my restraining rail. And again, you can see the concern about very high lateral forces. And again, you see that here. You can see how strong these braces are. And again, that's really a function of the concern about the level of lateral load. So again, what we're looking at is we're looking at the wheel. We're looking at the wheel sitting in here. And the back of the wheel coming up against the restraining rail.
Can I ask a question?
Yes.
About the distance between the restraining rail and the rail. You told me to see how I can calculate it in CCRTP, and I didn't find it. Do you have any other source that I can find how I can calculate it?
Yeah, let me find another reference. I thought there were a couple of references in what I sent you. So let me get back to some references for you.
Thank you.
Rena, if for some reason I forget, I don't remember, send me a gentle reminder. I'll try to remember. But
because it's a lot of argument between the American engineers and European engineers about this distance.
Yes, yeah. Yeah, there is some difference of opinion on how to do that. I agree. Okay, so restraining rail is, as I said, used for very sharp curves. Standards differ, so you'll see different metros have different standards. I've seen standards for restraining rail for radii sharper than 365 meters, going down to very, very, very sharp radii less than 90 meters. Again, so it really depends on the standards of the metro that you're working with. I think it's probably it's most common sort of in the less than 200 meter radius range, but as I said, I've seen standards as much as 365 meters. If you have the very, very short wheel flanges, so if the wheel flanges are relatively short, I've seen more application of restraining rail for short wheel flanges, because you have more protection against the wheel popping out when you have a large restraining rail in the background here. Restraining rails usually go past the point of tangency and into an adjacent tangent track. So if you have a tangent spiral curve, we see restraining rail coming into the tangent as well. It just doesn't stop right there. And the reason for that is, of course, as I've explained before, the transitions are actually where you see the largest lateral forces. So if you just focus on the body of the curve for your restraining rail, you can miss the worst case transitions, which is either coming into or coming out of, worst case forces coming into or coming out of the transition between the tangent and the curve. So it's fairly common practice to run a restraining rail out into the adjacent track. At the absolute minimum, at the tangent to spiral point, but again, because you're concerned, going in is not so much as of a problem, because you don't really start happening anything until you go into the spiral. But coming out of the spiral is where you have some concerns, because if the wheel if the wheel or the bogie is rotated coming out of the spiral, it may need a little bit of tangent to straighten out, which means you can get some very high lateral forces even at the tangent on the outside of the spiral or the transition. And so that's one of the reasons why you carry it into the transit track. I have seen some places that do double restraining rail on extremely sharp curves. And the reason for that is, on very, very sharp curves, you actually have forces going to the high rail, outside rail, and you have forces going into the low rail or inside rail. So you actually have a spreading type of force. The front axle of the bogie will generate forces to the high side, and the rear axle of the bogie will generate forces to the low side. And we see that type of splitting. So with very, very sharp curves, so let's say less than 100-meter radius or something like that, I know of some transit agencies that put guards on both sides. I'm not, that enthusiastic about that, but I do know you'll see that practice, and you'll see that in some standards. Okay. So now let's go right into the track. I'm going to start off by talking about direct fixation track. Direct fixation track, which is the most common type of ballasted track worldwide, is a ballasted track structure where the rail is mounted on direct fixation fasteners that are attached to a concrete deck, slab, or invert. And this is pretty much the standard method of construction for tracks on tunnels and aerial structures. And in fact, even in conventional railroads, we see a lot of this direct fixation track in tunnels. because if you want to put a deep ballast layer in tunnel, you need a larger diameter tunnel, which gets to be very expensive from a construction point of view. So a slab track, a direct fixation track, usually requires a smaller diameter tunnel than does a ballasted track. You'll also see some at-grade tracks. So, for example, the Chinese use a lot of direct fixation track on their high-speed rail. On the very high-speed lines, 350 kilometer per hour railroads, they do use a lot of this direct fixation track. So here's an example of what direct fixation track looks like. This one is a continuously poured direct fixation track. So basically what you have, and you notice this is on an open track here, basically you have a slab and you have these specialized fasteners. Now, one of the reasons why this is a unique type of system is because these fasteners, and these, by the way, these fasteners are called direct fixation fasteners. That's the term of art for these type of fasteners. These fasteners have to provide all the functionality of your ballast and fastening systems. So, for example, resiliency, dynamic load attenuation, noise and vibration attenuation. This is a slab. There is no resiliency in the slab. The slab is not very effective for noise and vibration attenuation. This slab is not designed to give you impact resistance or impact reduction, impact load attenuation. So all of that functionality has to be built into the fastener system. So usually you have very thick pad. Usually you have two pads, and I'll show you the components in a few moments. There are special noise and vibration direct fixation fasteners. There is specially designed if you have a noise and vibration problem. So for example, in metros, we know when we were looking at Tel Aviv, for example, we looked at certain classes of noise and vibration attenuation fasteners at one point before they went to another approach, a floating slab approach, which we'll talk about as well for noise and vibration attenuation. The other thing noticed here is adjustment for gauge and alignment and surface. You really can adjust. In ballasted track with sleepers, you can remove the fasteners, adjust the gauge. You can tamp up your ties to bring it back in vertical profile, or you can align your track using the ballast to bring it back in alignment. You don't have that ability in slab track. You don't have the ability to adjust the track geometry. Now, you can say, well, my track geometry is not going to degrade. I'm rigidly there. Well, first of all, your rail is going to wear. So right away, you're going to get gauge issues because your rail is going to wear. You can also get alignment issues. And as I think I said at the very, very, very beginning of my lecture, everything degrades and everything fails. I have been involved in the maintenance of direct fixation track often enough to know that components fail or degrade, and sooner or later you have to do adjustments. And so again, because we don't have adjustments in the slab, all my geometry adjustments goes into my fastening system. And again, I'll show you that in a couple of minutes as well. Here's another type of direct fixation track. Here again, you have a concrete slab with plinths put on top of it. We'll talk about all these designs in a few moments. And again, you can see the direct fixation fastener here. You can see this. You can tell already this is a much more complex system than you have in a concrete sleeper or a wooden sleeper. And even though many of the clips are exactly the same, the rest of the system is much more effective. To put this in perspective, If you look at the cost of a direct fixation fastening systems, they can be of the order of $100 to $200 per fastener. Whereas the fastening systems for a concrete sleeper maybe runs $20, $25, and the fastening system for a wood sleeper maybe runs $10, $15 per fastener per side. The cost of a direct fixation fastening system is about $100 to $200 because of all that extra functionality that has to be built into that fastener, because there's nowhere else to put it, because you can't put it in the slab. Again, here's another view of a direct fixation fastening system. So here you can start seeing some of the major components. There is, you can see there's a pad that's actually underneath the base plates. Here's your clip. This happens to be a fast clip, which you'll also see with concrete sleepers. There's the insulator for this insulator fast clip is very similar to what you have for a concrete sleeper. Everything else is different. You have this very large base plate. You can see there's the pads between the rail and the base plate. This is the plate hold down. So this looks like it's a bolt that was cast in place into the concrete insert, and then the plate put down, and then washers and nuts put down to hold this in place. Here's your shoulder for your clip. So again, you can see this is a much more complex type of configuration. Now you want a really complex type of configuration. This is a system that they use in Singapore, where, notice here we basically have this clip is designed to allow us to take the rail out, just like with a concrete sleeper. And this is permanently attached, well, not permanently attached. You can remove the bolts and remove the nuts and remove this. But in this particular configuration, it's designed to facilitate elimination of removal and replacement of the fastener as well. So you have one elastic fastener holding the rail down, and you have a second elastic fastener holding the plate to the slab. And in fact, this particular configuration actually had the equivalent of concrete sleepers put in place, and then concrete poured in between, which was one of the techniques for manufacturing this type of a slab track. Again, another type of fastening system. Here, if you look very closely over here, if you see the serrated plate and this little top plate underneath the bolt. So this, by the way, is the reverse of the other hold down fastener. This has a female insert that's embedded in that's cast in place in the concrete, and then this bolt comes down and screwed into the insert. And then there's this top plate, the serrated top plate and the serrated bottom plate. Anybody want to tell me what this plate's supposed to do? Oh, come on. Nobody want to tell me what the serrated plate is supposed to do? I just finished telling you there was no lateral adjustment on a concrete slab. So what does this do? This is my lateral adjustment. This, and I have one on the mating side. By unloosening the two bolts, I can actually slide this plate sideways, and I can, I can keep my insert in here, but I have some movement here. It looks like I have the order of maybe ±8, ±10 millimeters that I can move laterally to give me lateral adjustment. This is one of several different techniques that are used for lateral adjustment of the direct fixation slab track, because again, I can't, once I embed that female insert into the concrete, I'm not moving that female insert, I'm not moving this bolt. So to move my plate, I use this serrated configuration over here. That's one of several techniques. Another common technique that they use is to use a series of eccentric washers where you can rotate by rotating the eccentricity of the hold down. You can provide lateral adjustment. I think I have a picture of one of those a little bit later down in this presentation. This particular configuration, this is on an elevated metro structure, used precast slabs. So you can see the precast slabs that were brought in place over here, placed, and again, these are our direct fixation fasteners providing all the functionality that we talked about. So typically, a typical direct fixation fastener, the most common type, actually consists of a separate top and bottom plate with a very thick elastomer in between. This elastomer can be of the order of anywhere from 12 to 20 plus millimeters in thickness. Actually, I've seen them as much as 25 millimeters in thickness. So you have a top plate, you have a slab, you have a bottom plate, and this very large elastomer is designed to provide you with all the resiliency that's missing in your slab and in your rail. And in addition to that, you have a second pad, a much thinner pad between the bottom of the rail and the top of the top plate. That serves multiple purposes, including providing electrical isolation, a bearing surface or a wearing surface between the bottom of the rail and the top top plate, which is usually cast iron, even though in some cases it can be plastic. Of course, you have the insulators, you have a clip, and then you have the plate hold down and adjustment mechanisms. So here's another example. So this is actually has a separate top and bottom plate with an elastomer in between, and then there is an external coating provided on this entire assembly to keep it together so that you actually install this in one piece. You can see this is using a Pandrel fast clip. Sorry, E-clip. This is an E-clip. In this particular design, the electrical isolation is in the direct fixation pad. You notice there's no insulators on the base, on the toe of this clip. So the electrical isolation comes from this top coating. Here, you see an external insulator in the top of this, on top of this clip. Again, you can see in both cases here, both of these use a serrated washer system to provide lateral adjustment. Here you can see the one plate. Here you can see the separate plate. Actually, here you can see, this is a good picture because you can see everything here. This is my top plate, which is a casting, a very expensive casting, because you can see from the complexity. It also has to provide all of the shoulders for the clip to make sure it provides proper toe loads to the clip. There's the pad between the rail and the top plate. There's the pad between the top plate and the bottom plate. There's the bottom plate. And again, this has a female insert cast in the concrete. And then there's a bolt that comes down and goes into the female insert. And again, there's your lateral adjustment. Vertical adjustment is provided by shims. So usually you have shims that go underneath the bottom plate. So you would take off the bolt, you would insert shims and put them in there. And so a vertical adjustment is a bit of a complex exercise because of the shimming process, but that's usually how you do vertical adjustment because of shimming. Gauge adjustment can be accomplished, can likewise be accomplished by lateral adjustment. of each individual plate, since you can move one rail with respect to the other rail, and that gives you adjustment of gauge. Okay, here's just a different view. This is this plate that we're seeing over here. Again, this is actually this is actually an assembly system over here with a top and bottom one. You can see the fastener body consists of a ductile iron top and bottom plate that are fully vulcanized and molded with an elastic compound in between. So what you're seeing here is the vulcanized coating on the outside of the combined top, bottom, and elastomer. So basically, this whole area here is vulcanized and coated together. Again, here's how you can see it installed in the track. So typically, you would have in a single plate, which is one of these, you'll have 2 hole-bound bolts, 2 clips, 2 insulators, ductile iron top plate, bottom plate with an elastomeric pad, everything bolted, both can be molded together, female inserts for the anchorage, shims for vertical adjustment, etc.
What is ductile iron?
What is ductile iron? It's an iron. It's you know, when you get into the metallurgical definitions of steel versus iron, it gets into really what is the percent carbon that you have, what's the percent of other components. Ductile iron is defined to be a steel-like metal that's on the border between iron and steel that has a high level of ductility. So ductility, remember the definition of ductility? We talked about it when we did fatigue. If I take a sample and elongate a sample, so I do a stress strain diagram, I'm elastic up until the yield point, and then I'm plastic beyond that. So ductility is the amount of elongation I can tolerate. So typically, for example, for most railroad applications, ductility is around 10%. So ductile iron is basically, oh, I'm sorry, there's a typo here. There's a C there, it should be ductile iron. I didn't see that before. Did I answer your question?
Ductile, okay.
Yeah, ductile iron, sorry. I didn't realize I was missing the C there. Okay, so because of this very significant requirement for the direct fixation fasteners, because they have so much functionality, the specifications and the testing of direct fixation fasteners are really fairly sophisticated and fairly complex. So this is an example of a spec that I took from one direct fixation fastening system that's used in metro systems, just to give you an idea of what kind of fastener characteristics and testings do you need. So you can see there's a vertical stiffness of about 23 to 28 kilonewtons per millimeter. You notice this is kilonewtons per millimeter, not kilonewtons per millimeter squared. This is a classical spring. This is really, really important because some of the earlier design pads were much stiffer. Some of them of the order of 50 to 70 kilonewtons per millimeter, which turned out to be way, way, way too stiff and generated much too stiff a track structure. So the stiffness becomes really important. So this vertical stiffness is basically a quasi-static stiffness, which means you apply the load at low speeds. Your rate of loading is relatively low. Many of the new generation fastening systems also specify a dynamic stiffness, where the where you measure the stiffness under a very rapid dynamic loading, very high rate of loading. And the dynamic stiffness is usually about 1.5 times the static stiffness. So for example, if my static stiffness is 24 kilonewtons per millimeter, my dynamic stiffness would be about 36 kilonewtons per millimeter. The rail cant, of course, is built into the, I forgot to mention it, but of course the rail cant, the rail cant is of course built into the plate. Let me see if I can show that here. Here you can see it right there. You can see the rail cant is built into the plate. Again, it's virtually impossible to accurately put a rail cant into a concrete pour. So again, you build that into the direct fixation fastening system. Longitudinal rail slip, that's really a function of longitudinal fastener strength. So that's of the order of about 12 kilonewtons per fastener for this particular case. Repeated longitudinal loading and repeated dynamic vertical loading. So these are really, I'm going to say fatigue testing, but they're really repeated load testing. So you can see in this particular case where they specify plus or minus 9 kilonewtons for 1,000,000 cycles longitudinally. So longitudinally, so this is longitudinally in the direction of the rail. So we're looking at the longitudinal restraint of the clips in this particular case. And then vertical uplift. So this is a vertical uplift like force loading cycle where we're running about 9 kilonewtons for about 1.5 million cycles. Then you will very often see a maximum allowable uplift movement. So you can see here that where they specify a vertical force of 72 kilonewtons and a lateral force of 40 kilonewtons. So right away, you're looking at an L over V of what's that, 4/7. So that's an L over V of about 0.6. So that's enough to overturn the rail. So an L over V of around 0.6. Remember, we did this. By the way, make sure you're familiar with this analysis. You may see this again as well. Again, we covered this in the class, but an L over V about 0.6 is enough to give you your vector outside the base of the rail. So all of a sudden, this rail wants to overturn if it's not held in place by the fastener. So here again, we're accepting or we're accommodating this by allowing railhead movement must be less than 9 millimeters under this loading. And by the way, this is it is standard practice in designing metro systems with direct fixation track to develop this type of specification. This is a standard type of specification that will be used that going out with the tender for direct fixation track. Withstanding dynamic loading. So this is lateral and vertical loading. So this is dynamic loading where both L and V are applied. So you can see 62 kip vertical and 62 kilonewton vertical, 18 kilonewton lateral applied for 3 million cycles. So this is a case. Very often what happens here is you're actually applying a load that looks like that, where the lateral component's 18 kilonewtons, the vertical components are 62 kilonewtons, and you're running this for 3 million cycles. And by the way, for these type of loading levels, a test like this will take 2 weeks to run because you're really testing of the order of, maybe 2 hertz, 3 hertz at tops. So, so you're looking at 3 hertz, which is 3 cycles per second. To do 3 million cycles, that's 1,000 seconds. So there you got 3,600 seconds per hour. So all of a sudden you're looking at what? 300 hours or so. Electrical resistance check. Well, first of all, the first check, this is actually a current check, because remember, if you're dealing with a metro system, this is the third rail return. This is the power return for your for your traction power. So 15,000 volts DC. Again, it depends what your traction power configuration is. This was a DC system, so they did a 15,000 volt DC test. And then the actual electrical resistance, 500 volts DC, greater than 1 mega ohm when the system is wet and 10 mega ohms when dry. So again, here you'll be testing both under wet and dry conditions. So you can see the testing is actually fairly significant, fairly serious and fairly significant here. Again, just another variation of the design. You can see here there's a bottom steel plate just to add to the complexity. So I have a top plate, I have an interim plate. This is my top plate up here. I have an elastomer in here. I have a bottom plate over here, and then I have another steel plate on the bottom over here. So the variations of this are I'm not going to say infinite, but there are a lot of them. Okay. Now, given the sophistication of these fastening systems and their ability to attenuate dynamic loading vertically, they generally have poor to medium noise and vibration attenuation characteristics. So you have noise and vibration sensitive zones, becomes an issue. For example, when I was working on Tel Aviv Metro in the early stages, I actually helped them do a survey of noise and vibration sensitive areas. So it turns out that the Metro came near some concert halls, it came near some laboratories, it came near synagogues, and in fact, one of the extensions, not the red line, I forget which one, was going through a big hospital complex. It was actually coming right next to the CAT scan and MRI units, and they were extremely concerned about vibration affecting the CAT scan and MRI units of the hospital. So again, where the traditional noise and vibration performance of a traditional DF fasteners are not adequate, there are a secondary set of noise and vibration fasteners designed just for control. So there are two types. I'm going to show you a picture of those. This is the most common one. This used to be called the Cologne egg because it was developed in the city of Cologne and later became so widespread that they just called it an egg type fastener. And this fastener is very interesting because remember, with a traditional fastener, I have my top plate, I have my elastomeric plate, elastomer, and I have my bottom plate. And so my elastomeric fastener is 100% in compression. Well, it turns out that gives you, as I said, mediocre or moderate noise and vibration performance. In this fastening system, my top, oops, let me fix that a little bit. My top plate looks like that. My pad looks like that. And my bottom plate looks like that. So while in the center, I have my traditional compression, out here around the edges, and this is 360 degrees, not only, and my loading is here, not only am I taking this load in compression here, I'm taking this load in shear. So this elastomer going around the circumference of this pad is in compression and shear. And that additional performance, that additional shear performance gives us significantly improved noise and vibration attenuation results. It's been shown to reduce noise and vibration by over 10 decibels, which means cutting it in half. By the way, take a look at the serrations here. You get a very, very nice view of the serrations here as well. So that's one type. That's the one where you use a shear element. to do that. The other one is actually a fairly interesting design, relatively new, and kept becoming really quite popular in recent times. And this is one where the fastener does not touch the base of the rail at all. Let me see if I get a better picture. Here we go. So if we look at it from this configuration, you notice the fastener is not touching the base of the rail. The rail is sitting on an elastomeric pad over here, but there's no downward pressure from the fastening system. And in fact, the rail is supported primarily by the fastening system in the web of the rail. You can see there's an elastomeric element here, and this is steel over here. And the rail is supported 100% by this elastomeric element over there. Not 100%, but 90% or so. You can see it here in conceptual. There's that elastomer. There's the it's actually a cast iron. It's not a steel. It's a cast iron top plate, and the base is again really hanging up there. So this is an example of it in the field. And again, you can see the rail is really supported completely on the web of the rail. Another example, here you can see there's a little pad underneath the base of the rail, but that's just designed just in case there's some load that slips through. But most of this situation is designed through here. You can see this was actually in Madrid, where they're applying this this Pandrel Vanguard system. Hong Kong using it as well. Again, you can see the configuration here. I'm not sure there's even a pad underneath the base of the rail here in the Hong Kong configuration. I think the rail is completely isolated and completely supported up here. We also have direct fixation fasteners for special track work, which become much more complex. So when I said a regular direct fixation fastener costs between $100 and $200, direct fixation fastener for special track work costs between $200 and $400. Extremely expensive, because you notice this has to provide for the variation in the location of the fastener as you go through the switch. So if you remember on the diverging regular switch, the position of my fastener, my angle, my orientation, my position is changing. And I have to have this kind of adjustment built into the direct fixation fastener for the for special track work. Okay, now when we get to the subject of track modulus from our beam and elastic foundation analysis, among other things, obviously a concrete slab track is much stiffer than a ballasted track. And even with the presence of the elastomeric elements, we're still dealing with a very high level of rigidity. And, you know, the elastomeric elements in the fastening systems does something, but sometimes we actually have to introduce elastomeric elements into the slab construction as well. Okay. Now, how do we make, okay, so we pour a slab and do we put a rail, a DF fastener directly on top of the slab? Usually not, because usually the slab pour doesn't have the fine tolerance on it. So what we generally tend to do is we tend to use two different approaches in our slab, direct fixation slab track. We either use a cement grout pad like this, which is poured on top of the slab. So here's the concrete slab, and here's the grout pad that's poured on top of the slab, and then the DF fastener put on top of the grout pad. So in this particular case, in this configuration, each fastener has its own grout pad, and the construction tolerances are really set by in the grout pad itself. So you can have a little bit rougher construction tolerances for the concrete slab, and then you have the final tolerances in the grout pad. And then the fasteners are held into place by the anchor bolts. The anchor bolts go all the way down into the base concrete pad. There's no reinforcement, there's no reinforcing steel in these grout pads, but the anchor bolts do go all the way down into the slab itself. Here's another example. This is a slightly thicker grout pad, different configuration. This is the pour. By the way, there are two ways of building one of these things from a tolerance point of view. They're usually referred to as bottom up or top down. So bottom up, which I think is how this one was built, you basically pour your slab, you calculate your actual dimensions for your grout pads, you pour your grout pad to the tolerances that you need, and then you lay your direct fixation fastener directly onto the grout pad. That's bottom up design. Top down design is slightly different. You pour your slab, and then you come along with a fixture like this, where you position your rail, and then usually very often you'll attach your direct fixation fastener to the rail. So you have your rail with the direct fixation fastener, and you use the fixture to accurately align the tolerances between the bottom of the fastener and the top of the pad. So you're setting your tolerances on your rail, which is really where it should be. Oops, let me put that back over there. And you then pour your grout pads between the bottom of the DF fastener and the top of the slab, and that's a bottom down configuration. And I'm starting to see more and more top down. I'm starting to see more top down type of construction being used around the world, because it's actually a little bit more accurate. You can hold your tolerances a little bit finer when you use a fixture to hold your rail and fastening system exactly in location, and then you can pour your grout pad accurately between the bottom of your pad, the DF fastener, and the top of your slab. Okay. Okay, hold on a second. I'm gonna, in the interest of time, I'm not gonna go through the details of how you design and pour your grout pads through there. Again, you can see through here real quickly, the fasteners go down through the grout pads, and there's some discussion here that I'm just gonna skip because of interest of time. And I want to go to the second type of construction that we see, which is a concrete plinth. So instead of using a grout pad between the direct fixation fastener and the slab, we use concrete plinths, such as you see here. So here you see the slab, you see a concrete plinth, and you see my direct fixation fastening system. In this particular configuration, notice that one plinth holds multiple fasteners. I can see anywhere from 3 to 6 to 8. We've seen those in the field. Very typically between 3 and 6, but we've seen them up to 12. I think this is a very long one over here. And then you want to have your interruptions in the plinth just for, to give you cross drainage. So you can see your drainage. You can actually see your drainage mechanisms through here in your cross drains. There's another view. This is an egg type of fastener for noise and vibration reduction. And this is my running rail. And you can see my concrete plinth. Now the concrete plinth is usually reinforced, but not pre-stressed. So you use reinforcing steels, bars in the manufacture, and then you put your fastening. You know, your fastening now doesn't have to go all the way through into the slab, depending on the size of your track. So here's an example of two different configurations. In this particular case, the fasteners do not go into the slab. They just stay in the plinth. Again, you see the reinforcing steel in the plinth. In this particular configuration, the fastening systems do go into the slab. Actually, the plinth is, in this particular case, is actually cast partially embedded into the slab itself. So again, you see the different types of design. Okay, again, I'm not going to go into the details. You can read them on their own. How do you epoxy in place? A lot of these places are either cast in place or installed after the fact. On curves, of course, this is where your elevation has to come in. So this is a lot easier to put the elevation in the plinth than to try to put the elevation into your concrete slab. Trying to put the elevation into the concrete slab is much, much more difficult. You know, there are places where it's done, but again, putting it into the plinth, it gives you a little bit more flexibility in terms of manufacturing. If you have guardrails or restraining rails, then you need an extra wide plinth. Here's a restraining rail on the low rail. And again, you can see we have an extra wide plinth on the bottom with the bolts holding down both the restraining rail braces and the fastening system itself. Okay, so I'm not going to, and again, the cant is built into the slab, but generally speaking, you want to have a cant in your slab for drainage as well. Again, I'll let you read on your own for tolerances, but again, as I mentioned before, the vertical tolerance adjustments for the DF track usually uses shims. That's the most common technique. I have seen some fasteners with vertical height adjustment, but they're very rare. They're very difficult. They don't work very well. Most people I know use shims. And so if you're using shims, you got to be really careful what the maximum difference in elevation between adjacent fasteners, because you don't want to have a ridiculous amount of shims in there. When SEPTA and the Philadelphia Metro built their one of their elevated track with slab, it was called the Market Frankfurt Elevated. They built that about, I'm going to say about 15 years ago. They completely rebuilt that with a slab track and plinths design, and they had a major problem with maintaining vertical tolerances. The contractor did not do a good job in vertical tolerances, and so they had some fairly significant tolerance issues, ranging in range about 3 to 5 millimeters between adjacent fasteners. And what was happening is that the elastic fasteners that they were using, which were a Vaslow fastener, were failing in fatigue very, very, very early on. I'm talking within the first year of service. And so they actually had 55-gallon drums on the deck of the track, where they just used to throw the broken fasteners and come in every couple of weeks and replace them. until they finally had to come back and do a complete redesign of the entire structure because it's intolerable. So again, shims usually of the range of 1.5 to 12 millimeters are a little bit thick for shims. Again, 1.5, 3, maybe 5 millimeters, 6 millimeter shims are more commonly used. You got to be careful of electrical issues with your reinforcing in your plinths, because again, you have to make sure everything is connected to a negative ground. Otherwise, you have problems with corrosion, and very quickly you can have stray current corrosion and failure in the reinforcing bars. Okay. Let's take a few-minute break right now. I think we're running a little past my normal break time. So let's take a couple of minute break and we'll continue. Let's take 15 minutes and we'll continue in 15 minutes.